Okay, have I started sharing? Not yet, right? Just a second. Okay, good. So we are done with the Stokes parameters and characterization of polarized light. The important concept, as you may have sort of guessed, is this sense of coherence, and the fact that most of the instruments actually measure intensity rather than the amplitude, at least in the optical frequency. So right, so in that case, Stokes polarization, Stokes parameters determine everything for your light, all the properties of your light, whether it's polarized or unpolarized. You cannot tell apart light sources which have the same Stokes parameters. Okay, so now we will actually go to a little more on electromagnetic theory, and this is sort of like material where we treat radiation. So I'm not actually going to deal with all nitty-gritty mathematics. It's a very highly mathematical topic, a little tedious. So it must be a revision for most of you, but I'll actually state the results and I'll sort of motivate how you get it, but I'll not be able to derive them in gory detail. So I encourage you to read the book and something like Jackson or Griffiths to understand the parts that I'll not be able to fill in. Okay. Okay, so let's start with the next topic. So this is okay. So electromagnetic potentials. So we are all familiar with electrostatic potentials very, very well, but even with electromagnetic potentials, when the magnetic field is and charges and currents are time dependent, you can describe the magnetic fields, electromagnetic fields, in terms of the potentials. So let me actually write down. So these fields are scalar potentials, electrostatic potential, and the vector potential A, which is a vector. Okay, so potentials actually. So let me write down the Maxwell's equations once more. So del B is equal to 0. What this implies is that you can always write B equals del cross some vector field, which is called the vector potential. Okay. Okay, and this is Faraday's law. Right, and the right hand side we can use the vector potential to write as, right, so this is basically what we can write is del cross E plus 1 by C dou A dou T equal to 0. So what this means is that we can write electric field as follows. Right, it's some sort of a gradient of a scalar field. Okay, or in other words, electric field is equal to minus grad phi minus 1 by C dou A dou T. So this is how magnetic fields are obtained from the vector potential, and this is how electric fields are obtained using the vector potential and the scalar potential. Okay, normally we have done a lot of electrostatics. This time dependent part is 0. But for radiation, the time dependence is very, very crucial. Okay, good. So basically, once we solve for phi and A, we can solve for B and E easily. Okay, so these are these two equations are already satisfied. What about the other two Maxwell's equations of del dot E equals 4 pi rho, where rho is the charge density, recall. So if we plug in this form for electric field, what do we get? We get del square phi plus 1 by c tau dot t of del dot A. Right, this is just the divergence of electric field is equal to minus 4 pi rho. Okay, so this is the so this is one of the equations. So we can actually write it in a slightly different form, a suggestive form. Plus 1 by c tau dot t of del dot A plus 1 by c tau phi tau t is equal to minus 4 pi rho. It's the same equation. I've just added and subtracted this term. Okay. Okay, so this is for this one. Now I have done this so that I get something like a wave equation. I already know that I can get a wave equation for the potentials, because we know that Maxwell's equations, at least in vacuum, have wave solutions. So we should be able to get, in vacuum where rho and j are 0, we should be able to get del square phi minus 1 by c squared tau 2 tau t squared phi equal to 0. So this is what I have written. The fourth Maxwell equation is for, this is the third, this is the fourth, del cross B equals 4 pi by Cj. So this is the current density, and then the displacement term 1 by C dou E dou T. So I'm actually writing these equations where rho and j are all charges, including the bound charges. I have not introduced this dielectric parameter epsilon, right? So these include all the charges and all the currents. Okay, so what about this equation? If we substitute for A here, what we get is, so B is del cross A, so we have del cross A is equal to, and then we have this, so this is the first term. Sorry, let me raise a little bit. This is the first term. Now this minus 1 by c dou E dou T is what we want to write. So minus 1 by c dou E dou T will give you, so let me just write this down and then I'll tell you how we get it. Dou T grad phi plus 1 by c dou A dou T is equal to 4 pi by c times j. Okay, so this is nothing but minus 1 by c dou E dou T. So minus 1 by c dou E dou T will give you this cross term for phi and something like a wave equation for A. So and we know that this is a vector identity. We can write this as minus del squared A, right, plus gradient of del dot A. Right, so these you can actually just prove by writing the expression for these in Cartesian coordinates, right? You know how del cross a vector is defined and so on, and you can actually show that in general these two are equal. So I'm actually not going to derive all those because you have already done it. So what we have is something which looks like the following: del square A minus 1 by c squared now 2 by now t squared A minus gradient of del dot A plus 1 by c dou A dou t. No, sorry, dou phi dou t. Because it's this cross term. Just a sec. Okay, so this is equal to 4 pi by c j. Again, this is like a wave equation for a vector A, and this is the term which is almost the same as what appeared for the equation for phi. Okay, and we know that potentials are not unique, right? There is something called a gauge freedom. So if we change, for example, let me just write down this gauge freedom is very useful to know about freedom. Basically, you have some freedom to choose your potential so that the equations become easy. So basically, if you change A, if A goes to A plus grad psi, and if phi goes to phi minus 1 by c dou psi dou t, right? If we have A as this, magnetic field is just del cross A, right? And del cross A, just del cross gradient of psi gives you 0. Similarly, the electric field. So basically, this gives the same B, right? Even though your A is changed like this, you get the same B. Similarly, if your phi goes to this, what you get is electric field is minus grad psi, minus grad phi, and minus 1 by c dou dou t grad of psi. Okay, so you will, because of this dou dou t, so you'll have this, this will also give you same electric field. Okay, so you can always add such a scalar function psi to these vector fields, and this is called gauge freedom. Okay, now this gauge freedom can be used to simplify the equations for phi and A here. Okay, and what is the gauge freedom that we can use? We use something called the Lorentz gauge, in which this term is 0. So del dot A plus 1 by c dou phi dou t is equal to 0. So this is the gauge choice that we make. So we choose psi such that this is satisfied. And this gauge is very, very useful when we are dealing with electromagnetic waves. In other problems, other gauges are more appropriate. Okay, so let's see, what does it mean? So, I mean, you can actually easily show that if you take del dot, so suppose you have a which does not satisfy it, you can always add this psi, this function psi, so that A prime equals A plus grad psi. And if you take the divergence of this, you get del square psi. And if you take dou dou t of this, you get a dou dou t of phi. And so basically you can always solve for psi such that this is satisfied. Okay, so this is the nice thing about Lorentz gauge, and what it does is these messy looking terms can actually go away if we have Lorentz gauge. And what we have are the wave equations for the electromagnetic potential. So wave equations for A and psi. What are those equations? Since this goes away, the wave equations are del square pi minus 1 by c square del dow 2 by t square phi equals minus 4 pi rho. This is the first one, and this is del square A minus 1 by c squared dow 2 dot t squared A equals minus 4 pi by c j. Right, so this is like a nice looking wave equation with the, so this is inhomogeneous because you have these right hand side which is non-zero. Okay, and we know how to solve these, right? The standard technique to do this is using Green's functions, and I'm actually not going to do it, right? Because this is like a standard calculation that we do. I have some homework problems where we sort of where I have asked you to work the details out, and yeah, so we'll get to that in the homework problems. Okay, so this is this, and what are the solutions? Solutions of these equations? The solutions are the following. Phi as a function of position and time. This is a field, so it's a function of r and t. This is equal to integral rho. This is the charge density. Let me just write down d3 r prime over, integration over some volume r minus r prime. Okay, so this is the solution for your potential. So let me actually just draw what r and r prime are. So basically, let's say you have some volume. Okay, so this is your coordinate systems. This is your point. You are sort of basically integrating over the whole volume. Okay, in fact, the whole space. So basically, wherever. So let's see. This is your r prime. This is the variable which is integrated over. So you're basically summing over all the charges. Okay, and what is r? R is this place where you're interested in finding the potential. So that this is where you're interested in finding. Sorry, my straight lines are a little bad. Actually, I should undo it. So this is my. Let me just mark this as the point. Okay. So this is the point P where I want. So this is R, right? And this is R minus R prime. So this is the point where I want to know the value of potential, right? So this is the expression for this. This is nothing but rho integrated over this whole volume, and you divide this. And this square bracket that I have indicated here means that this is called, we write it as RET. Basically, this means a quantity evaluated at retarded time. So what is retarded time? Now, so this is the position, this is the center of your coordinate system. You want to know the potential here as a function of, as a function of r and t, right? But because of this wave equation, the wave nature of this equation, the Green's function is such that it must take into account the fact that the charge here, right, the field here at the present time t is caused by the charge at r prime, not at the present time, but at a time which is smaller than the present time by this light propagation time. So retarded time is basically t retarded right? T retarded is equal to the time now when you want to measure the field minus this distance r minus r prime divided by c. Okay. In fact, if you take this form and if you substitute back it in this equation, you will see that this is satisfied. But it's actually quite tedious because you have to do complicated algebra. Okay, so you see the retarded time is not only a function of t, it is also a function of r prime. So if you're at a given r prime, you have a slightly different retarded time and compare, because it sort of corresponds to the light travel time from the point r prime to r. This is clear?
Yes, sir.
Yes, sir.
And is there anyone in the class who has never done this before? Please speak up if there is someone, and I can actually suggest where to look this up. So, Griffiths does it and Jackson does it, and every standard advanced E&M book does it. So I encourage you to brush up this stuff. So this is for the scalar potential. What about the vector potential? Vector potential is given by a very similar expression, except that you have 1 by c and you have j. And this again is calculated at the retarded time, d3r prime divided by r minus r prime. Okay, so it is important to understand what these formula mean, right? What it means is that if you want to calculate field here at time t, you look at the charge at every position in the source of the charges and currents, but not at the present time, but at a slightly earlier time, and you sum the contribution from all of them up, and with a weighing factor like 1 over r minus r prime. So this is all that this is saying. The expressions are very, very similar for the potential. For example, in case of electrostatics, for example, you don't have this time dependent term, right? If you don't have this time dependent term, you get a similar looking Green's function and a similar looking expression for phi, except that there is no retarded. You don't have to worry about retardation because in electrostatics, del square phi equals minus 4 pi rho. You're basically assuming that the information propagates instantaneously. So that's why the retarded time need not be considered. Or in other words, C is infinite. So you don't have to worry about the difference between time at the position of the measurement and the time in the source. But here it's very, very important. Okay, that's why the nature of equation. So this equation is something called an elliptic equation, right? Whereas this is a hyperbolic equation. Hyperbolic equation involves propagation of waves and information, whereas elliptic does not have time appearing in it. Okay, good. So, right, so any quantity q, if I use this square bracket and I write retard here, what it means is that this quantity q is evaluated at r prime, but at a time which is slightly shorter. This is called the retarded, retarded quantity. Now, mathematically speaking, both if you have a plus sign here, then also you can show that these equations are satisfied. Instead of the minus sign here, even if you have a plus sign there, these equations will be satisfied. So that's called an advanced potential. But because of causality, we choose the negative sign rather than a positive sign, acausal. The reason being, right, changes here can affect field here only after some time, not before, right? You know, if something happens here in the future, that should not affect the field here before that, right? Okay, so this is the formal way of finding phi and A, and once you have phi and A, you can use these expressions for, you know, so these expressions for calculating the fields. So dealing with potentials is much easier than dealing with fields. But once you have potentials, you can easily get your fields using these formulae. Oops. Okay, so now, is this clear? Okay, good. So now we will, so this was for a general distribution of charges and currents. But we can actually, so let me, okay, so let me create some space and continue here. Okay, so let's see, single moving charge. If you have a single moving charge, what happens in that case? So here we were considering some charge distribution, extended charge distribution. Now a simpler case is a single moving charge. So suppose you have a charge whose trajectory is given. So you don't know, you have some charge which is moving in certain way, and this is the coordinate system. Okay, and let's say so this is its location at some time r0. So the trajectory is called r0 t. Okay, so this is the location of the charge at given time t. Okay, and so it, you know, this, so this, the value of location is here, here, here. This is sort of the trajectory. Now we are interested in finding. So we again, so you know, you have to remember this is a charge. So you know, charge is zero everywhere except at r0, right? Because it's a single charge, not a charge distribution. So now we want to look at, you know, let's consider some point P where we want to know the field. So again, okay, so this is your R. Okay, and this is point P, sorry. Let me get rid of this dot. Oops. No problem. Okay, so this is the setup. You want to know the potential at point P, given that a charge moves and whose trajectory is given by r0 as a function of time. Good. So this is again, let me draw. Okay, so this is called yeah, so this is just that r minus, so this is r minus r0. Okay, now this at point P we are interested in time t. Okay, so this time is actually not you know, I mean, generally if we want to calculate the potential at time t, we are actually interested in this time which we call t prime or t retarded. So let me call it t prime. So at this time when we are measuring the potential here, the charge would actually come here, right? It would have moved along its path, and this is let me call it, this is r0 at actually t, the same time when we are interested in measuring the potential potentials at P. Okay, good. So let's see. So this is trajectory. So what about the charge velocity? So charge trajectory is given. So R is equal to R naught T. This is the charge trajectory. And what about charge velocity? This is nothing but R dot dot, right? How does position change with time? This is position of the charge. This is the velocity of the charge at a given time t. What about the density field due to this? Rho is nothing but, this is just a delta function, right? Q. So if the charge is Q, this is the charge density corresponding to that. R minus R naught T. Right, so this delta function has a dimension of 1 by volume, because if you do a delta function times dV, you get 1. So this is the charge density, and the current density is nothing but Q U. U is nothing but R naught dot delta R minus R naught T. You have to be careful with the dimensions. So this is charge per unit area per unit time, right? Because delta function is like 1 over volume, so length per unit time. So it has the correct dimensions. Okay, so this is the charge density. This is the current density, and of course you can actually verify that Q, Q is equal to integral of rho d3r. Right, so if you integrate the charge over the whole volume, charge density over the whole volume, you should get Q. And similarly, Qu is the current, and that's equal to J R T T3 R. This is the total current. This is the total charge. This is the current density. This is the charge density. Okay, very, it's, a lot of this is actually just about understanding what these equations mean. The notation is important to pay attention to. Okay, so this again is the time now. This is the position of the particle now. This is position of the particle at a slightly earlier time, which corresponds to this light crossing time. Okay, so let's see. So potential. So the expression for potential will be using the same. What is potential? Potential, I will not rewrite the expression. This is the potential, okay? What I have to do is I have to calculate the charge density, not at time t, but at a slightly earlier time. So let me just write this down. And we know that this is the charge density. So let me write this down. Okay, so this is equal to Q integral of delta R prime minus R naught T prime. So this T prime is slightly earlier than time t by R minus, oops, so this is R minus R prime and D3 R prime. Okay, when what is T prime? So this phi is a function of X and T, and we are, or R and T, sorry, not X. And what are we doing? We are just integrating over all these, all the volume R prime, and we have just sort of substituted for rho as that. And what we have to be careful about, this is like rho, this is like this is rho R prime, okay, but So, you recall that rho has to be evaluated at this time, not at time t. Right? So, what is t prime? So, and what is r naught t prime? So, r naught t prime is such that r minus r naught t prime, absolute value of that. So this is just the distance, right? This is r minus r naught. This is t prime. This is at not time t. At time t, this is here. So this is r minus r naught t prime is equal to c times t minus t prime. Okay, what I'm saying is that this distance is equal to the light travel, it's c times the light travel time from this point to this point. So this relates t and t prime for a given t prime. Okay, so this is the integral that we have to evaluate. So what do we do? What we are saying is that you have to just sum up all these delta functions. Since you have a single charge, you just have to sum up this at the location of this charge at a slightly earlier time. Right? That's just q over r minus r prime evaluated at an earlier time. In fact, that's what, yeah. So let's actually do it mathematically. So this is fine. This is just, so what we can actually do is we can write phi is equal to, we can actually introduce another integral here. So, let me just write this. So d3 r prime, this is the volume integral, and then I introduce an integral over time, dt prime. Okay, all the retarded times. But I then actually introduce a delta function such that, so t prime minus t plus r minus r prime by c delta r minus r naught t prime divided by r minus r prime. Okay, so what I have done is I have just introduced this time integral, right, which just sort of says that this t prime, right? So if you have an integral like this, right, when you integrate over t prime variable, what it does is it makes this quantity evaluated at a time such that t prime equals t minus r minus r prime by c, right? So this is just like a simplified, just a mathematical way of imposing what we want. And we can actually call this as capital R, right? So we can, and this is nothing but capital R. Okay, and this of course is a function of t prime, because just a sec, let me clarify. Oops. This is R, and this is the vector R, this is R. Okay, and this R prime is actually this integral integration variable, right? This t prime is, integral over all possible times, retarded times, and this delta function imposes that relation between capital R, T prime and T. Okay, so let's see. So we can actually do the R prime integral first. So let me actually see my notes. Yeah, this is a little tedious. All you have to do is just be a little careful with what is meant by these various symbols. Okay, so what I'll do is I'll do the R prime integral first. So let me just write first and then I'll explain. So this is Q dt prime delta T prime minus T plus R minus R naught T prime by C divided by R minus R naught T prime. Okay, so this is, let me explain what this is. See, if I do the R prime integral first, here R prime is a variable, it does not depend on T prime, but this delta function is such that if I do this D3 R prime first, I have just you know, so what are the things that depend on R prime? This one and this one, and right, so that's it, right? This and this is what depends on R prime, but my R prime is such that R prime is evaluated because of this delta function. My R prime is evaluated at R naught T prime, and that's what it does, right? When you do a integral over a delta function like this, right? So this something like what you do is you just evaluate the integrand at the value where the delta function vanishes. So that's what makes this R prime R naught T prime, and that's what makes this R prime R naught T prime. Okay, so now we don't have R prime anymore. What we have, those R primes have become R naught T primes. Okay, and that R prime integral has been, has been done. Got it? Good. So this is your phi. Okay, good. So right, and R. So this is nothing but R. So let me just write this down again. So this is Q integral delta T prime T plus R by C. This is RT prime, right? This is dependent on the retarded time. D3 prime divided by RT prime. Okay. Right, so RT prime, right, RT prime is equal to C times T minus T prime. Right, this is just the definition of this retarded time. Okay, and we can actually do one more change of variable so that this delta function becomes a little more easy to handle. So what we do is T double prime. So we set this argument of delta function as my new variable t double prime. So t double prime equals t prime minus t plus r t prime by c. Okay. So in the end, this should be a function of position and time. And the position dependence is in capital R, and this t prime is integrated over, so time dependence is here. Okay, good. So if you have this, then your dt double prime. So your time is fixed, right? You're looking at a field at a given time t, but your t prime sort of can change because you're looking. So if you're looking at the charge position here, you're looking at earlier times. Right? At earlier times, you have to consider capital R to be this, and so on. So at a particular time t, this is the position. But the field at this time is not just contributed by the position of the charge here, but at everywhere in principle. So that integral does that. Okay, so this is dt double prime is equal to dt prime. So time is fixed. So this is not differentiated. Plus dr dt prime 1 by c. Okay, so this is the change of dt prime. Okay, so this r here is just the mod of this vector r. So let's see. So r squared is equal to r dot r. Like when I don't write a vector sign, it is a scalar. It's absolute value of that vector. So twice r r dot. Now this dot is with respect to t prime. This is what I'm trying to calculate. Dr dt prime is equal to twice r dot, right? I mean, this is just the first. I mean, I'm just taking the derivative on both sides. This is how this goes. And what is capital R dot? What is capital R dot? So recall, capital R is r minus r naught t prime. So r is equal to r minus r naught t prime. So r dr dt prime is equal to minus r naught dot, right, evaluated at t prime. So this is nothing but minus twice r dot r naught dot at t prime, which is nothing but u at t prime. So this is equal to minus twice r dot u. Everything is evaluated at t prime at the retarded time. So basically, what do we get? We get r dot is equal to minus r hat dot u. Okay, this is important. And this r hat is also sometimes called, this is the direction, is also sometimes called n hat. The direction of the location of the particle at the retarded time connecting the point of observation is the direction n hat. Okay, so this is this is nothing but minus n hat dot u. Okay, so this is your r dot. So let's go back to this change of variable that we were trying to do. So phi rt is equal to now we have q integral delta t double prime, right? So that's just the argument, and dt prime is nothing but, so this is equal to dt prime times 1 right, so this is also called minus n hat dot beta C. Okay, so beta is nothing but U by C at the retarded time. This is used quite a bit in special relativity, this beta. So dt prime 1 minus n hat dot beta. Okay, and this, the book uses this, calls it kappa. So just remember these. So this is so dt prime equals dt double prime divided by 1 minus eta e n hat dot beta. Okay, and what else? And capital R t prime, so divided by R. Right, so this is what we have. And now we have actually a simple thing. So when you have an integral like this, all you do is evaluate the integrand. So when you have delta x, so when you have an integral like delta x fx dx, I mean, this just means that your integral is basically f0. You evaluate the integrand at the value of x where the argument of delta function vanishes, right? So in the same way, we just evaluate the integrand at the retarded time, when the t double prime vanishes. That's just q by r times 1 minus n hat dot beta, and this is evaluated at the retarded time. Okay, so you get a very, very similar expression as you have for potential in electrostatics, except for this 1 minus n hat dot beta factor in the denominator. The vector potential calculation proceeds in almost the same way. Okay, because instead of q, you have q u by c, but everything else is more or less the same. And the main thing is this delta function manipulation. So your ART, the vector potential, is in a similar way given by Q beta divided by R 1 minus n hat dot beta. Again, this is evaluated at the retarded time. Okay, so this is vector potential, this is scalar potential. Once you know these at a given position and time, you can take the partial by partiality and curls, and you can get gradients and get your electric and magnetic fields. So these are called Liénard-Wiechert potentials. Liénard potentials or retarded potentials. Okay. Now, it's interesting to notice some things, right? This factor in the numerator, 1 minus n hat dot beta, this is very, this is let me create some space. So this 1 minus n hat dot beta factor basically means that if beta is close to 1, right? If a particle is moving relativistically, so beta close to 1. Of course, beta can never touch 1. Massive particles can never approach, never become C, travel at C. So when beta is order 1, this factor, if n hat, that is the line connecting the charge and the observer, right? So is along the direction of the motion of the particle. So this is the direction beta, and this is the direction n hat. Then this 1 over 1 minus n hat dot beta, or 1 by kappa, can actually be very, very big. It can be very large. Okay, and this is sort of the signature of relativistic beaming. So basically the potentials and the fields and so on are very, very high. So if you have a charge, right, which is moving relativistically, then most of the radiation and most of the fields are actually in the forward direction. So this is called relativistic beaming. Okay, it depends on the details, but this is a generic result that most of the energy is radiated in the forward direction, and this factor 1/1 minus n hat dot beta signifies that relativistic beaming. Right. If you guys have followed this imaging of the black hole research, you see that the disk is brightened on one side compared to the other. The reason for that is actually relativistic beaming. The plasma is moving close to C, and the material which is moving towards us gets relativistically boosted. Okay. The other thing is, so this is about relativistic beaming. The second part is radiation. Right, so how do you get radiation? Recall that if you have phi like this, Q by R is, in electrostatics we get Q by R, right? And when we take the gradient of it to get the electric field, we get 1 by R square, right? But for radiation, we need E and B going like 1/R. How do we get that? We don't get that because of this factor. No, in fact, we get it because R is not just equal to small r, but it is equal to r minus r naught t prime. Right. So when we are evaluating like a gradient of this phi, we have to evaluate at a time t. So that makes that puts an implicit dependence, dependence of r on t prime, and that's what gives you radiation. It is this term which gives you radiation, because if it is not there, all you get is E going like 1/R square as in electrostatics. But because t prime and t are not the same, because of that, when we take gradient, we have to take a gradient such that R is fixed. Okay, so this gives you radiation. So this retardation is very, very important for getting radiation field, which can carry power to infinite distances, right? The property of radiation field is that the Poynting flux goes like 1/R squared, and the total E dot is actually constant. So the radiation can carry energy to very, very far distances. Okay. And of course, once you have phi and A, you can calculate B. Okay, so let's go to the next topic. So what's the time? Oops. Oh, wow. No. Okay, let's go to fields now, electric and magnetic fields. Till now we were talking about the potential. So let me actually just write down the expression for the fields. Fields. Right, so all you have to do is use this, right? A, B equals del cross A. Now I had a expression for A, and now I can get B. So E is equal to -1 by C dou A dou T minus grad phi, right? So once you know phi and A, you get E and B. Okay, but the calculation is actually very, very tedious. You have to be extremely careful when doing these del cross and gradients. right? Because of this retardation time, implicit dependence between r and t prime. So let me actually just write down the expressions for E and B. Okay, these are well-known expressions, but one should derive these at least once in their lifetime, just to, go through the very, you have to be very careful in the mathematics. Okay, so this is q n hat minus beta 1 minus beta squared by kappa squared, kappa cube r squared. So this is the expression for electric field that I'm writing. So this is all these square bracket things are evaluated at retarded times, and q by c plus q by c n hat cross n hat minus beta cross beta dot divided by kappa cube r, and this is again evaluated at the retarded time. Now, so this, this is electric field, and similarly magnetic field is actually, once you have the electric field, magnetic field is just n hat cross E, but evaluated at the retarded time. Okay, now what does this mean? Now here we have 1 by r, here we have 1 by r cube. This is called the velocity term, term, and this is called the radiation or acceleration term. Right, you recall beta was the instantaneous velocity at the retarded time. Beta dot is the acceleration, right? Time, acceleration is beta dot times c. Now, when we plug your a and phi from the previous expression into these, this is what you get. Okay. So velocity term decays very fast. It goes like 1 over r square, right? When your r r is much bigger than the length over which your charges are, and this r square is just 1 over r square. So this cannot carry a lot of energy far away. This is not the radiation term. This is called the near, this is called the near zone, not the radiation zone. But when this term, which has acceleration appearing here, is the radiation term. This term has an electric field which can carry energy to very far distances. This expression says that then, so again, the geometry you should remember. So you have, right, so this is the point where you're observing. This is your R, right? So this is, let's say this is the position at the present time, but this is at the retarded time, right? So this is slightly before, this is your capital R, T prime is your retarded time, and R is equal to C times T minus T prime, and this is also equal to R minus R naught T prime. Okay, and this vector R is equal to R minus R naught T prime. Okay, so and you can actually see, right, B is perpendicular to n hat and E, right? Because it is like a B n hat E hat. They are like n, if you do E dot B, that gives you 0. If you do n hat dot B, that gives you 0. B is perpendicular to n hat and E hat, right? For example, when we did plane waves, we saw that K, E, and B form a triad. So it's sort of a similar relationship. And this term, so when your beta is small, right, the velocity term is sort of, for your, if beta is much less than 1, kappa is 1, right? So let me just write down what was kappa. So, and this direction is n hat. This is equal to r n hat. And what was kappa? Kappa was 1 minus n hat dot beta, or everything is at retarded time. So kappa is order unity, beta much less than 1, r is like capital, small r, the position where you're measuring. So your electric field goes, it has the same expression. So n hat minus beta is just n hat because beta is much less than 1. So q n hat by r squared, right? This is just a electric field due to a point charge, right? Electrostatics, basically. So this is like a generalization. This velocity term is a generalization of Coulomb's law when the charges are not static but moving. And you get Coulomb's law for beta much less than 1. Now, the interesting thing is that the velocity term gives an electric field which is along, so let's see, just a sec. All right, so let's sort of consider the velocity term a little bit more. Okay, so you have a charge here at time t prime, and at time t it reaches here. So this is r naught t prime, the first position, and the second position is r naught at time t. Okay, and this is your observation point, and this is n hat. Okay, so this is your point P where you're measuring. So this is r n hat. Okay, and what is this distance? This distance is just c. This distance is nothing but v, right? So beta c. Beta is a vector. So let's just consider a straight line motion for now at constant speed. So the acceleration term is 0. Beta dot is 0. So this is t minus t prime. All right, so this is the distance traveled in this time. What is r? R is, here, is nothing but c times t minus t prime. So this is equal to c t minus t prime n hat, right? And what is this? So let's see this guy. Let me use a different color. This is a triangle that I have formed up. What is this? This is this plus this is equal to that. So so this is r n hat minus, what is ct minus? That's nothing but r beta, right? So this is nothing but r n hat minus beta, right? So basically what it means is that this electric field, which is pointing in n hat minus beta hat direction, is actually for constant beta, right? The velocity field, the electric field due to the velocity term is along the line joining the present position and the and R, basically, and R. You see the interesting thing? We are calculating everything at the retarded point, but because of this n hat minus beta, the electric field here is actually in the direction connecting to the instantaneous location of the charge, right? This is just interesting. So this is about the velocity field. What about the acceleration field? So let's just write E rad, just the acceleration part. This is equal to, R, T. You have to be extremely careful about what is meant by all this mathematical expressions. After that, if you're careful, things are not that, although they appear very complicated, their interpretation is not hard. N hat cross n hat minus beta cross beta dot. This is the acceleration term. Okay, and again, B, the radiation, is nothing but n hat cross E, radiation evaluated at the retarded time. Again, here, say in this, the velocity term can have an electric field which is along n hat. So E, B, and n hat are not triad in general. But for the radiation term, n hat, E hat, and B hat are a triad. How do we see that? You can see that n hat dot this is 0, because this is n hat cross some other vector. So E is perpendicular to n hat, and B is perpendicular to n hat and E rad. So they are triad like the plane wave in vacuum solution, right? So these n hat, NEB form a right-hand triad. And the other thing is the absolute value, right? If you take E rad, this is equal to B rad, because n hat, E, and B are perpendicular to each other. So if you take absolute value, it's just absolute value of B is equal to absolute value of E. Just like this is also consistent with the solution of plane waves in vacuum. The E0 and B0 were equal.
So the second term is the radiation that contributes to radiation.
Which second term? Yes, this one.
In E, the second term, n minus B vector. Okay, thank you.
This one, yes. This is the radiation part of electric field. This is the velocity near zone electric field. Okay. Now, how do we see this geometrically? So there's a famous construction that is sometimes drawn for seeing this. So consider let's consider a particle which is moving with constant velocity. Okay, so this is a particle moving with constant velocity beta c. Okay, and we know that the field due to a constant velocity particle moving at a constant velocity is always joining the present location of the particle, right? So the field due to this, say at this time when the particle is here, okay, is actually, the drawing is a little hard. So let me actually do one thing. Let me open the book and try to see, because the drawing is a little hard. Maybe I can actually try. Let me try, and if it doesn't work out, we'll see. So let's say we are measuring the right. So what is the electric field due to this charge at this place, at all places, everywhere? It's sort of, it's given by the line joining, right? The line joining the observer and the present location of the particle. So this is like a electric field. So these are like equally spaced. It's isotropic. So these are field lines basically. Okay, so these are field lines. Oops. Okay. Now, oh shoot. Just a sec. Ooh. Okay, so this charge was moving in this direction, and suppose this charge, would come here after some time, from here to here. After a time, I mean, this distance is beta times time delta t. Okay, let's say this charge was stopped instead of traveling, so it traveled with beta c at all times. Okay, so it had a constant E field. It had an E field which was joining the point of observation and the present location of the charge. And suppose this charge was stopped here, so it was just instantaneously stopped at this point. Okay, so the far field electric field still doesn't know that the charge has stopped. So this is the distance beta delta t. The far field doesn't know that the charge has stopped, but the near field knows that it has. So how do I draw it? So let me actually draw this this thing. So this is beta delta t, and this is say beta c delta t, and this is c delta t. So this is very fast moving particle. So light would travel till here, right? And so beyond, so the fact that the charge has moved from here to here. Okay, so this is at time, some initial time. This is some time delta t later. So the outside world, outside this red hemisphere, sphere, doesn't know that the charge has stopped, because information takes time to propagate. So for those guys, the field will still be radially connecting this point to the outside. So how do I draw this? Actually, this is where the trick is. So and the points which are inside do know that the charge has stopped. So if the charge has stopped, it's all radial. So let me actually just draw these radial field lines. Right? If beta is 0, you just become, you're just sort of like Coulomb's law. This is your electric field inside. Okay, whereas outside, let me use some other color. Whereas outside, they don't know that the charge has stopped. So they, the lines will point like this towards this location. So you have, you have this. Sorry. This is the location. What am I doing? So, so okay. So let me just say this in words. So outside field will not know that the charge has stopped. Okay, so it will keep pointing at this location. Outside field will point at this location. Inside field, the charge has stopped, so it will be along the black lines. So there is sort of like a, so let me open this figure in the text and then try to motivate it.
So it means they have different origins, means for inside and outside.
Yes. So let me open Wiki Enlightenment and go to that page. Okay. Yeah, the drawing part is a little hard. Okay. Yeah, so that we are actually in chapter 3 now. Yes, here. So let me actually explain it here. Right, so the charge was moving at constant speed, a constant velocity at time t equal to 0. At some time it just stops at x equal to 0. Okay, and had it not stopped, it would have reached this position. Okay, now the outside world beyond this light travel region does not know that the charge has stopped. That information that the charge has stopped has not propagated out. So this sphere that has been drawn here is just c times this time difference. Okay, and this charge is moving close to the speed of light, so that's why it's almost touching this sphere. Now these lines which are outside are connecting to this position at x equal to 1, right? You can actually see they are connecting the x equal to 1 line because outside world still thinks that the charge is moving at the constant velocity. So these are the, you can actually see the outside lines are connecting to x equal to 1. But the inside world, which is in causal contact with the particle, will have radial fields, just like in electrostatics. Okay, so when you join these fields, what you see is the only way to join this field and this inner field is to have this large tangential field. Right, you can actually see these are the field lines. So outside, magnetic field goes like 1 over r squared, falls like 1 over r squared. Inside, electric fields and magnetic fields fall like 1 over r squared. But here you have transverse magnetic fields which are perpendicular to the direction n hat. Right? These are all different n hats. These are transverse fields which are much stronger than 1 over r squared. Okay, and how do we see that these are stronger than 1 over r squared? So this distance is c times delta t. This delta t is time between this point and this point. So this time is c times delta t. So electric field outside and inside goes like 1 over r squared. Now we have to conserve flux. So if you apply Gauss's law, along this. Can I open the two things together? Just a sec. How do I show that? So E here goes like 1 over R instead of 1 over R squared. And the reason for that is, I can't even write. So let me actually go back to where my notes were, because here I cannot annotate. That's actually a little irritating. It slows down actually. Oof. Okay, let me do one thing. Let me just try to Google. Let me just try to Google electromagnetic field to point charge stopped radiation. Let me see if I get some nice. Okay, good. We may have some good illustrations. Yeah, so this is right. So this is from Rebeckian-Lightman on type thing only. Right. So this is like beta equals 0.8. So outside world lines connect to. You can see what I'm showing on my screen, right?
Yes,
Yes,
sir.
sir.
Yes, sir.
Yes,
Right.
sir.
This would have been the location. So the blue lines are there. The red lines is where they know that the charge has stopped and I better be radial with respect to the stationary charges location. Now, this is fine. But how do you show that this is 1 by r? So see, both this field goes like 1 over r square, this field goes like 1 over r square. Now the trick is, how do we show that this is 1 over r? So this width of this guy, right? The width over which the field lines are in the transverse direction basically is the time scale over which the charge takes to stop, right? So this charge cannot stop instantaneously, otherwise this is a delta function. So if there is a time delta t over which the charge stops, that's the width c delta t of this region. Now, if we apply flux conservation, right? So here it's sort of, here the area goes like r square. Here, if we consider like a Gaussian pillbox here, so the the area goes like this c delta t, the width of this thing, which I said is c delta t. Delta t is the time scale over which it comes to rest instantaneously. So if that delta t is not this time from here to here, the delta t is the time over which this guy decides to stop. It goes from zero, beta to zero on that time scale. So this area, if we consider a Gaussian pillbox here, like, it's actually difficult.
Sir, actually, one question.
Yeah. Yes.
If it come to rest with a velocity, uniform velocity, then there will not be this thing, right? Because I mean, it has to be some acceleration for
No.
radiation.
It is moving with the constant velocity. Okay. At some time, it just stops. Right.
Okay.
It goes from v to
To
zero.
zero.
Right.
Okay.
At that time, in that instant, when it comes to rest, it is accelerated. Right.
Okay.
So that's why you have electric field only for that portion of time when it comes to rest. You don't have any radiation field here. You don't have any radiation field here. You only have a pulse, which corresponds to the time over which it decelerated to come to rest. Okay.
Yes, sir. Thank you.
So, if you consider a Gaussian pillbox like this, and if you apply E dot ds equal to 0, this area is like r square, whereas this area is like r times delta t, and delta t is just the time scale over which it takes to stop. So this electric field, it actually goes like 1 over r instead of 1 over r square. I'm sorry, I cannot really, I should have prepared this a little better, because the drawing is hard. But the key point is that this electric field strength does not fall like 1 over r square, but 1 over r. That's why this can carry energy to very large distances. Right? In this particular example, it's just a pulse, right? Because the charge accelerated only for a short time when it went from moving to rest. Okay. So I will actually. Sorry about this. I should have had a better way to handle it. But anyway, I hope you got the point, right? In the far zone, the charge, the rest of the world doesn't know that the charge has come to rest. In the inner zone, all positions know that the charge has come to rest. So there is a discontinuity in the electric field, and that's where you have this transverse field, which is much stronger than the Coulomb field that we are used to. Okay, so we'll actually end here. So let me stop recording. Any question?